Good morning, my dear students. My name is Anjaneyulu, working as physics lecturer in one of the reputed institution. Today, our concept is about electric potential. Okay, so our concept is electric potential. Very important concept for all competitive exams and also for intermediate. Okay, electric potential. Potential means the inner stamina of the body, right? So the inner stamina of the body we call generally potential. For example, you see, if your book is on the table, say some height 10 meters, so you want to take it down. So certain amount of work is to be done in bringing the book from one height to another height. Similarly, when you are moving a test charge in the electric field, certain amount of work is to be done, right? So the amount of work done in bringing a test charge from one point to another point is called potential difference. Or else you are bringing it from infinity to closer to the body, it is called electric potential. So this is one definition. Or you can also call potential as the level of charging. Electrical potential is also called level of charging. So the more charge you give, the more potential it will show. Just like you take one glass, pour some water into the glass, then the water level will increase. Similarly, when you are adding charge to your body, automatically the potential will increase. But Earth is a huge reservoir of charges. It is having lot of charges. So by adding a small charge or by removing some small charge from Earth, its potential is not altered. So that is why potential of Earth is always taken as 0, only as a reference to find potential of other bodies. Okay, so now we are going to know how to find electric potential. So we are using calculus methods to find the electric potential of a charged body. Okay, so the aim of this derivation is electric potential, due to a point charge. So potential is defined as work done in moving a charge. Say potential energy at a point, say P, minus potential energy at infinity by test charge. Or else you can also write work done by moving a test charge in an electric field is called electric potential. So now we are going to know electric potential due to a point charge. So now you consider a point charge, at point O. So now you are bringing, say a test charge which is at infinity brought to closer to the charged body, say at a distance R. So work done in bringing this test charge somewhere at infinity to closure. So work done in bringing the test charge from infinity closer to this charged body is nothing but electric potential. So now we are going to calculate electric potential due to a point charge. So consider a point charge, Q at a point O. So this test charge Q0 is brought from infinity, infinity to closer to the charged body, say at a distance R. So for our convenience, let us assume this test charge Q naught is brought through a small distance, say dx, in opposite direction of this electric field. Okay, so work done in this process. Okay, work done in this process, work done is Fs cos theta na, so F ds cos 180. Because you are bringing the test charge in opposite direction to the electric field, right? So that is why theta taken 180 degrees. Cos 180 degrees value is minus 1, right? So dW is equal to F dx with minus cos 180 value minus 1 na? Next, F means force between this point charge and the test charge one which you brought closer to the charge body, right? So according to Coulomb's law, force between 2 point charges, remember Q naught by x square. So let us assume the test charge Q naught is somewhere at x distance into dx. Okay, so this is the small work done in bringing the test charge through a small distance. But you want to know the total work done in bringing the body from infinity to closure. So we have to integrate now, integrating on both the sides between the limits. So infinity, because it brought from infinity now to closure to the body, say R. Okay, so integral dW equal to W now, yes, minus Q naught by 4 pi epsilon naught, right, into integral dx by x square. Okay, so we have one formula in integration for x power n. Over here you have given 1 by x square, so you can take it into numerator now. So you will get x power minus 2, right, dx. So x power n integral value, x power n plus 1 by n plus 1. So here n is minus 2 now. So minus 2 plus 1 by minus 2 plus 1, right? So you get W is equal to, okay, minus Q naught by 4 pi epsilon naught, right, into x power minus 1 by minus 1. Now minus 2 plus 1 by minus 2 plus 1 now. So this minus cancel. And about limits, it is brought from infinity to R now. So that is why lower limit taken as infinity, right, upper limit taken as R. Okay, so work done is equal to Q naught by 4 pi epsilon naught, right, upper limit minus lower limit now. So that is why 1 by R minus 1 by infinity, right? So 1 by infinity, 0. Okay, so work done, work done is equal to potential into charge now, because potential is defined as work done in moving charge, right, in an electric field. So that is why work done taken as potential into charge. So that is why this equal to Q naught by 4 pi epsilon naught now into 1 by Q naught cancelled. So thereby you get potential due to a point charge at a point is given as 1 by 4 pi epsilon naught into Q by R. Okay, so very important formula to calculate electric potential at a point. Okay, how to calculate electric potential at a point? Remember 1 by 4 pi epsilon naught into Q by R. Q is the point charge which you have taken. No? So due to this point charge, what is potential at this point? 1 by 4 pi epsilon naught into Q by R. Remember, potential is a scalar quantity. It is similar to energy now. So that's why it is a scalar quantity and measured. Electric potential is measured in volt. Okay, so volt is a unit of electric potential, or you can also measure in joule per coulomb. Work done by charge na, work done units, joule per coulomb. Okay, suppose if there are number of point charges. Okay, so you want to find the electric potential due to many charges. So remember, potential at a point due to more number of charges will be definitely sum of all the charges. Okay. Now, suppose there are some point charges. Okay, say Q1, Q2, Q3, Q4 and so on. Okay, say this Q1 is at a distance R1. Say this one at a distance R2, R3, R4 and so on. Like this there are some point charges. So you want to find potential at this point due to all these charges. Okay, so total potential is equal to sum of all the potentials. Okay, so just now we come across one valuable point, that is electric potential due to a point charge is given as 1 by 4 pi epsilon naught into Q by R na. So first one, say Q1, you know 1 by 4 pi epsilon naught, okay, into Q1 by corresponding distance, say R1, okay, plus, you know 1 by 4 pi epsilon naught will be common for all, right? So that is why I have taken in the beginning only outside. Okay, now about V2, you know 1 by 4 pi epsilon naught, charge say Q2, corresponding distance R2, okay. Now next one, Q3 R3, remember including the sign you should say. Suppose you have given some negative charges, so sign also must be taken while adding the potential. Okay. Next Q4 by R4 and so on. Say plus Qn by Rn. Okay. So this is the total potential at this point due to all these n charges. Now about electric potential. Okay, electric potential due to a dipole, due to an electric dipole. Okay, so just now we derived electric potential due to a point charge. Now about electric dipole. So dipole means you all know that is there are 2 point charges na, say negative, positive separated under fixed distance 2a. No? Now at a point you want to know its electric potential. So the aim of this derivation is electric potential at a point due to a dipole. Say this positive charge, okay, is at a distance R1. Say negative charge is at a distance R2. So from this point it is R. Okay, so now aim of this derivation is electric potential. Okay, electric potential at a point due to an electric dipole, say at a distance R. Okay, so you know due to positive and negative will give you the total potential. So you know total potential at point P is 1 by 4 pi epsilon naught, right? Q by R, no? So here positive Q na distance R1. Next, second one, 1 by 4 pi epsilon naught, right? Q by R2. Negative na, so that is by minus. So total potential due to positive negative at this point is 1 by 4 pi epsilon naught Q by R1 minus 1 by 4 pi epsilon naught Q by R2. Okay, so if you know this 1 by R1 and 1 by R2, by substituting we can find total potential. So 1 by 4 pi epsilon naught, right? Q also you can take common now. So 1 by R1 minus 1 by R2. Okay, first we are going to know about R1 and R2. R1 by geometry wise, R1 square, okay, is equal to A square plus R square, okay, minus 2AR cos theta. Because this is the direction of dipole na, so that is why A square plus R square minus 2AR cos theta, because it's positive one na. Next, about R2 square, okay, R2 square by geometry, A square plus R square plus 2AR cos theta. Okay, so it is about R1 and this one about R2. So these are R1 square and R2 square. Okay, by simplifying this now, we can find the total potential. So R1 square is equal to, okay, so if you are taking R square common now, so it will be A square by R square, right, plus 1 na minus 2AR cos theta by R square. Okay, so 1 R gets cancelled now, so you will get R square of, okay, A square by R square plus 1 minus 2A cos theta by R. Okay, so A means distance from midpoint of the dipole to positive 1, small one. Dipole means two opposite charges separated under small distance. So A is very small. So A square is too small. So one small value by a large value will always give you a small value only. So that is why this part is neglected, because you are taking at some long distance, right? So that is why A square by R square part is neglected. Okay, so you get R1 square is equal to R square of, okay, so 1 minus 2A cos theta by R. Okay, now you apply square root on both the sides. Okay, so you get R1 is equal to R of, right? So 1 minus 2A cos theta by R whole power 1 by 2, because you applied root on both sides now. So this is about R1. You want to find 1 by R1, right? So 1 by R1 is equal to 1 by R, right? So 1 minus 2A cos theta by R whole power minus 1 by 2. Okay, reciprocal. No? So this type of expansions we usually do in binomial theorem. Okay, so whenever there is 1 plus x power minus n now, it can be taken as 1 minus nx and so on. No? So here n taken as minus half now, So that is why you get 1 by r1 is equal to 1 by r, okay, so plus 2a cos theta, right, by r into 1 by 2, because n taken as minus of na, so 2 cancel. That is, you are neglecting all the other terms, because you know a is very small value, so a square by r square cubes all are neglected, okay. So you get 1 by r1, okay, that is equal to 1 by r of 1 plus, okay, a cos theta by r, okay. Similarly, you can take r2 also, right? So you know r2 square, okay, r2 square, that is by taking r square common, okay. So you will get r2 square equal to r square of 1 plus 2a cos theta by r now. Next, okay, that is when you apply square root on both the sides. So you take reciprocal, okay. So whenever reciprocal you are taking 1 by r of 1 plus 2a cos theta by r now. Next, minus. So in place of 1 by r2 you get 1 by r of 1 minus a cos theta by r, okay. So now you can substitute, right? So you know potential at a point is 1 by 4 pi epsilon naught now, 1 by 4 pi epsilon naught into q by r, no? So you know potential at a point is, you know, q by 4 pi epsilon naught of 1 by r1 minus 1 by r2, no? So q by 4 pi epsilon naught common. So in place of 1 by r1, you know, you get 1 plus a cos theta by r, okay, into 1 by r, okay. That I will write other side also, otherwise we will write here, okay. So that is about 1 by r1, right? Next, about 1 by r2, no, minus minus plus na, so a cos theta by r, okay. So you know this minus 1 plus 1 gets cancelled. So you get potential at point P is given as, you know, q by 4 pi epsilon naught, right, a cos theta by r plus a cos theta by r, together you get 2a cos theta by r, into another r is there now, so it will become r square, okay. Remember, dipole moment is always given as length into charge, which we derived in the previous class. Remember, electric dipole, 2a into q will give you potential, and this is a dipole moment, no? So 2a into q I can write p na, 2a into q I can write p, okay. So you get potential at a point is equal to this 2a into q, I am writing dipole moment, okay, dipole moment into 4 pi epsilon naught, okay, into cos theta by r square, okay. So this is the dipole you have taken, minus q plus q, okay. So at a point P, dipole, due to dipole, potential is P by 4 pi epsilon naught cos theta by r square. See, suppose you want to find on axial line. See this point, you are taking the axial line. Then you know this theta will be taken 0. Okay. So potential, okay, on axial line. So if you are taking it on axial line, no. So the point, if you are taking it on axial line, theta is 0 now. So cos 0 value 1. No. So that is why it is P by 4 pi epsilon naught, right, into 1 by r square. Suppose the point taken on equatorial line. Okay. Equatorial means, you know, the line which passing through midpoint of the dipole. So in that case, okay, equatorial, if you are taking, you know, it is P by 4 pi epsilon naught na cos theta. Now 90 degrees, no. So cos 90 value, you know, 0 by r square, but you know, this total 0. So remember, electric potential due to dipole on axial is P by 4 pi epsilon naught into 1 by r square. But whereas on equatorial, it is 0. Now, about the given problem, that is, there are infinite number of charges, each of magnitude given 2 microcoulomb. Okay, so they are placed at 1 centimeter, 3 centimeter, okay, 9, 27 and so on. Okay, so you want to find the electric potential at origin. See, this is your given problem. Okay, infinite number of charges, 1 unit, they are placed at 1 unit, 3 unit, okay, 3 square units, 27, no, 3 cube and so on, right? So you want to find potential at origin. Okay, so you want to find the electric potential at origin due to all these charges, and they said consecutive charges are in opposite sign. Say first one is positive, then second one minus, next plus, minus. So in this way they are arranged. Okay, so you want to find potential at origin. So we know potential due to a point charge, we derive, no, V equal to 1 by 4 pi epsilon naught, right, into Q by R. Okay, so potential due to all these charges you want to find at origin. Okay, so Q is common now, so I can write 1 by 4 pi epsilon naught, okay, into Q. Same, no, that is 2 nanocoulomb, nano, multiple, all of you know it now, minus 9 coulomb, okay, into 1 plus 1 by 3 plus 1 by 3 square, 1 by 3 cube and so on. But over here you have given a condition that opposite sign na, so first one positive, then second one must be negative, again negative. So in this way they are arranged. See, plus q minus q plus q minus q, right? So all of you know the value of 1 by 4 pi epsilon naught, that is, you know, 9 into 10 power 9, right? Next 2 nanocoulomb na, so that is why 2 into 10 power minus 9. But if you see distance given in centimeter, you must convert into meter na, so that is why in the denominator, okay, in the denominator you can write 10 power minus 2, because these are all centimeters na, you must convert into meter, right? So 1 minus 1 by 3 plus 1 by 3 square minus 1 by 3 cube and so on. Okay, so if you notice, it is a geometric progression. So sum to infinite series. So I hope all of you know this formula. A by 1 minus R. A, where you know A is first term and R is common ratio, right? So first 1 minus common ratio means second one by first one. But here minus sign that's why minus of minus 1 by 3. Okay? So when you further simplify 4 by 3 multiplying, you get 3 by 4. Right? 4 by 3 reciprocal 3 by 4. Okay? This total value you get 3 by 4. Okay? So you know minus 9 plus 9 cancel 18 into 10 power 2 taking into numerator, right? 3 by 4. So you know this divides 2 times and this divides 9 times, right? 27 by 2 into 10 square. So you know it is nothing but 13.5 multiplying with 100, 1350 volt. So what is total potential due to all these charges at origin? 13. Now about the given problem. So potential changing given by an equation V equal to 5 plus 4x square. So potential, electric potential is changing with respect to distance, position. Okay, so you want to know force experienced by a 2 microcoulomb charge when placed at distance of half meter. So you are placing the charge body, okay, in an electric field whose potential you have given. So you want to know force experienced by it. So you know whenever you place a charge body in the electric field force experience is EQ, right? So whenever you are placing a charge body in the electric field, how much force you will gain? EQ. So E you want to find, but instead of E you have given V. No? So what is the differential form of E? You know E equal to minus dV by dr. No? Change of potential to change of distance, position, right? So if you are differentiating this, you can find the electric field strength, right? So you know electric field strength E is equal to, okay, minus dV dou V by dou X, okay, minus dou V by dou Y into J minus dou V by dou Z, means partially you are differentiating with respect to X. Thereby you can find Ex, Y, Ey, Z, Ez. Okay? In this way you can find the strength of electric field. So first we'll differentiate this function partially with respect to X. Okay? So first I am going to find dou V by dou X. So when I am differentiating partially with respect to X, only X is to be considered, remaining all taken 0, right? So that is why you know minus, okay, minus differentiation of any constant 0 4x square differentiation, right? So 4 into 2x, right? So minus dou V by dou X is equal to minus 8x. You want at half meter, right? So X must be taken half okay, so it is about you know Ex. Okay, now similarly we are going to find the other two also. So now differentiate this function with respect to y. Okay, so minus dou V by dou Y. Okay, so constant 0, right, plus 4x square. See, you are differentiating partially with respect to y. Then x will be treated as constant only, no? Not only x, z also treated as constant. Okay, means this is also 0. Say EY. Okay, next minus dou V by dou Z. So constant differentiation 0 plus that 4x square differential value also 0. Why? Because you are differentiating with respect to Z. That means only Z is to be considered, remaining two, x and y treated as constants. Okay, so Ez is also 0. Means strength of the electric field, okay, is minus 4i, okay, the remaining two are 0. So electric field strength is known to us. Okay, now you want to find the force experienced by the charged body when it is held in the electric field. Okay, so force experienced is EQ na, E, okay, minus 4. They said they are placing a negative charge, no? So that is why minus 2 micro, multiple minus 6 na, so minus of minus plus, right, into 10 power minus 6 unit of force, Newton. Means when you are placing this 2 microcoulomb charge in the electric field of strength minus 4 units, it will experience a force of 8 into 10 power minus 6. Okay, so here you need to remember that differential form of electric field strength is given as minus, okay, dou V by dou R. Now about the given problem. So you have given strength of electric field vector, okay, E bar is equal to 40I plus 60J. Corresponding units are also given in SI system, that is Newton per Coulomb. Okay, so you want to find the potential at a particular point. Okay, so position vector you have given 3I plus 3J. Okay, so you know in vector form, okay, so E is equal to minus dV by dr, na? Or else you can also write V is equal to minus E bar dot R bar. Okay, so remember potential is a scalar quantity, okay, scalar product of strength of electric field and position vector. Okay, so electric potential at a point is given by dot product of electric field strength and position vector. Okay, so electric potential V is equal to, okay, so dot product of minus of these two na. So I hope all of you know about dot product A1 A2 plus B1 B2 na. So 40 into 3, okay, plus 60 into 3, okay, so minus of, right, 120 plus 180. Okay, so 100, 200, 300 volt, because they are given in SI system only na, so that is why corresponding is also given in. Now about the given problem. So you have given a graph such that distance taken along x-axis, okay, potential taken along y-axis. So you want to find the intensity of electric field, or you can say electric field strength. Okay, at a particular point you have given 5 meter. At this point you want to know electric field strength. So you know slope of this graph means V versus D gives electric field strength now. That is, you know, E equal to minus dV by dr, means difference in potential by difference in distance ratio will give us electric field strength. No, nothing but you can say slope. Okay, so you want at phi now, so this line slope itself will give you dV by dr. But you see its projection given along y side means negative only, no? So in this way if you are taking, it would be positive, but projection given along y axis. So that is why E is equal to, okay, so minus of minus, okay, so difference in y quadrant 5 units na by difference in x quadrant 2 units na. So difference in y quadrant 5 units by difference in x quadrant. This line slope only you want to find now. So y by x, slope remains same at any point. So 2 units. Cancel now. So you get 2.5 units. Okay. Potential if you have given in volt now, if this is in meter, you can take volt per. Now about the given problem. So in this problem also you have given potential function, okay, that is minus x square y, okay, minus xz square plus 4. Okay, so you want to find the electric field strength at that point, means at x, y, z. Okay, so you know, in order to find x coordinate of electric field strength, you must differentiate this partially, right, with respect to x na partial differentiation. So while differentiating, you know, only x is to be considered, the remaining or treated as constants in case of, you know, partial differentiation. So minus, okay, so x square differentiation, you know, 2x na, but y treated like constant, so y only, okay, minus differential value of x 1 na, okay, into z square, okay, plus constant value 0, okay, so this is all multiplied with minus, okay, so x quadrant of electric field strength will become, you know, minus of minus plus na, so we'll get 2xy, okay, plus z square. Okay, now about EY means electric field strength of y coordinate, right? So same procedure, but you are now differentiating partially with respect to y, okay? So this is equal to, now only y you have to consider, x square or x anything will be treated as constants, right? So minus x square into differential value of y 1 na, okay, minus over here there is no y term, that means it will be treated as constant, so differential value 0, constant you already know 0, into minus, right, minus of this now, so you get minus into minus plus now, so x square. Okay, now last one, that is you are differentiating with respect to z. Okay, so Ez is equal to minus dou v by dou z, means you have to now differentiate partially with respect to z, right? So the other are treated as constants. No? So differential value of x square y is 0. Why? Because you are differentiating partially with respect to z now. So that's why that would be 0. Plus next one, x as it is, z square differentiation 2z na, plus constant 0 into minus. Formula wise na. So minus of minus plus na, you get 2xz. Okay, so you know Ex, Ey, Ez. Therefore, electric field strength vector, okay, will become, you know, 2xy plus z square into I na, plus second one, you know, x square into j, plus last one, you know, 2xz na. So this is the strength of electric field vector. So suppose you have given, instead of x, y, z points values, you can substitute. So thereby you can find the strength of electric field. Thank you for watching this video. Please subscribe my channel so I can give you more and more information. Even advanced level also I can teach myself. Okay, so I am requesting all of you, please subscribe my channel so that I am going to give you all topics that are related to electricity, modern physics, okay, and about waves, ray optics, all concepts almost. Okay, thank you.